All right, so let's take a look at this example. So we have a uniform ladder of length L, so they're giving us the length, and it makes an angle theta relative to the floor, so we have a theta here. The top of the ladder leans against a smooth frictionless wall, and we want to find the minimum angle theta min between the floor and the wall that will allow the ladder to remain at rest if the coefficient of static friction between the floor and the ladder is mu s. So that's the information we're given. So I noticed one thing that they don't give us is the mass of the ladder, but it does not say that it's a massless ladder or a negligible mass ladder, because if the ladder was of a negligible mass, then you could put the ladder at any angle. So the fact that it's not massless is important. But the fact that they don't give us the mass either means that Mrs. Humes made a mistake in writing the problem, and you're supposed to have the mass, or that the mass will probably cancel out somewhere along the lines. So kind of going through the steps that we need to do to solve this problem. The very first thing we need to do is to sketch a picture and identify our assumptions. So, which is what I've just done with you. Okay, so I've made all those assumptions. And then we're going to identify and label the forces. So now that we have an understanding of the problem, I'm going to assume that since this is a uniform ladder, that the force of gravity of the ladder is going to act at the middle. So I'm going to have a force of gravity here. Because there's not another person, I can just label this FG. I don't need any other subscripts. And then there is going to be a normal force over here with the wall. So I'm going to call that FNW for Fn of the wall. And then there is going to be a normal force here with the floor. So that's going to be Fn of the floor. And then there is friction here. And so kind of like we talked about just a minute ago, is that the tendency of this ladder is to fall down. So therefore this point has a tendency to go out. So therefore I need my friction force to point towards the right, towards the wall, in order for the not to fall down. So we have this friction force. Now one thing to be careful of is whenever you have multiple normal forces is recognizing that I'm going to call this FF so that I know that this is the friction force of the floor. This is the normal force of the floor. If there was a friction force with the wall, then that friction force would correspond to that normal force. I would call that one like FW or something along those lines. So that way I know that this is a pair. So when I define friction force of the floor, that's going to equal mu s Fn of the floor. Now at a physics 1 level, you're not going to have a crazy amount of variables. For example, if this was a wall with friction, it's likely they would give you the same coefficient of friction for both because it'd be simpler. But definitely the problems you see in physics C is they will give you different coefficients for each of these surfaces, which just makes it a lot bulkier with your variables. So those are the forces that we have acting. So once we've identified and labeled our forces, we need to choose our axis of rotation. So like I said, that one of the things that we need to consider is when doing our axis of rotation is it is definitely best to choose an axis of rotation that can eliminate as many forces from having torque. So as you look at this, picture where you think would be the best location maybe for that. Well, I would say the best location for this axis of rotation is probably here with the floor. That is probably a really good location for the pivot point, because that would mean that neither the friction force or the normal force with the floor are exerting torque. So that means the torque due to the normal force with the wall has to exactly equal the torque due to the gravitational force, because this one would cause a torque in that way, because if I do something like that, that's going to cause a rotation in the opposite direction. So that's where I'm going to choose my axis of rotation. Then I need to make sure that I actually label my lever arm values. So the lever arm value for FG is, so it's R for FG, is going to equal L over 2. And then if I were to do L for FNW, I'm going to have that one here. So R for FNW is going to equal L. And then I also want to identify my clockwise and counterclockwise torques. I've already kind of done that. So The FNW is going to be the one in the counterclockwise direction, which gives a positive torque because my thumb would point up out of the page. And then if I were to look, the one due to gravity here is going to be negative because not only is it causing a clockwise rotation, but if I were to use the right hand rule curl there, my thumb would point into the page, which is negative torque. So all of that I've done as set up before I've written a single equation. Well, I guess I did write an equation here. That's just a reminder though. So your setup is the most important thing, even more important than when you're drawing free body diagrams because of the necessity to identify lever arms. So one thing I suggest is don't make these diagrams too teeny tiny because we still need to like resolve some of these forces into components. And when you do that, your diagram is going to get very busy. So I do suggest making sure that you draw bigger diagrams. And if you need to, draw your forces bigger so your components aren't as small. I might go back and increase the length of these to make them a little easier to see. So once we have identified our forces, identified our axis of rotation, identified which forces cause torque, the lever arms associated with them, then we can write out the conditions for equilibrium. And this is where I would start every problem. So I would define that my net force in the x direction has to equal 0, my net force in the y direction has to equal 0, and my net torque has to equal 0. Because if I'm working an AP free response question, there are often points associated with defining the conditions of equilibrium. And showing that they're equal to 0 is different than just saying that, oh, well, my upward forces equal my downward forces, okay? Showing that they have to add up to 0 is the condition for equilibrium. The condition for equilibrium is not that certain forces are equal to each other, it's that the total sum of the forces add up to 0. So I usually start with the force equations just because I can handle that a little easier because I do it more often. So in the x direction, my net force in the x direction is going to be the positive force, which is going to be my force of friction. My FNW is going to be in the opposite direction, and those have to add up to 0. In the y direction, I'm going to have this FNF in the positive direction. And then in the negative direction is FG, and those have to add up to 0. And then with my net torque, like I said, my net torque, I usually do my counterclockwise then my clockwise. So counterclockwise would be the torque due to FNW minus the torque due to gravity. And that has to add up to 0. Please, in this step, do not skip writing the just in general torque. Same with these guys. Sometimes what happens is you guys get confident with your problem solving abilities and you start skipping, you start subbing in variables, but sometimes you make a mistake, especially with angles, and you sub in the wrong variable. It is important that you have a correct net force or net torque equation in each direction that is true, even if subsequently later on you substitute in something wrong. So please do not skip this step. Very, very important step. So the next thing I want to do is, once I've subbed in my variables, written my equations as I want to sub in my known variables. So I want to, if possible, get all of these in terms of things that are known. So I'm allowed to have L, I'm allowed to have theta min, I can have mu S, and that's really it. I can also have G, because G is a universal constant. This didn't specify that, but on an AP problem they would specify your allowed universal constants. So I'm going to define here that my force of friction is going to equal mu SFN. And I'm going to set that equal to FNW. Okay, so I've got that right here. Here I'm going to set FNF equal to mg. Now, even though I don't know what mass is right now, like I said, I don't remember 100% if I've made a mistake and left off mass or if it cancels out. So I'm going to leave that m in place, and hopefully it'll cancel out or at some point in the end. And then the torque due to FNW is going to be FNW perpendicular times R FNW. And that has to equal the torque due to gravity is going to be FG perpendicular times the R due to FG. Okay, so I'm going to do that right there and kind of go through and work more. So one thing I notice as I go through is I look at all my unknowns. I do notice right here that FNF appears in both of these two locations. So if I wanted to, I could eliminate FNF right away by subbing an MG. So I'm going to take this FNF equal to MG and sub it in right here. So I get that mu S mg is equal to FNW. So I basically eliminated the need to include this equation anymore, which is going to give me a little more room to work out over here. Now FNW perpendicular. So let's take a look at that. So this angle right here is theta min. So this angle over here is going to be theta min. So if I want to find the perpendicular component of FNW, it is going to be the opposite side of this triangle right here where FNW is the hypotenuse. So it's going to be based on sine. So I can define right here that FNW perpendicular is going to be FNW sine of theta min. Our FNW is L. FG perpendicular, let's see, that one's not quite as obvious. So, because I need to find the perpendicular component right here. But if I look, and this is a right triangle here, if this is theta min, this angle right here is 90 minus theta min, which means that because this is a right angle right here, that this angle right here is going to be 90 minus theta min. Hey, so that is actually going to be theta min right here. So that's just like any ramp, so that angle is theta min. So if I wanted to then find the component that's perpendicular though, that component that's perpendicular is right here. So this is FG perpendicular. That's the adjacent side of this triangle where this right angle right here is theta min. So that means that's based on cosine. So the perpendicular component of gravity is going to be mg times cosine of theta min. And then RFG is L over 2. So one thing I noticed right here is that L actually does cancel. So I have that L canceling right here. So that gives me that FNW sine of theta min is equal to mg cosine of theta min times L over 2. So I can actually come over here and like stick a 1/2 in front right there. So let's make that theta min is equal to 1/2 of mg cosine theta min. So now I notice that I have FNW sine of theta min. Well, FNW I have over here. So if I take my definition of FNW and plug it in right here, I get that FNW is mu s mg sine of theta min is equal to 1/2 of mg cosine of theta min. Whew. Oh, this is a good result because this means that mg is on both sides. So mg actually cancels out. So Mrs. Humes wasn't wrong. I didn't forget to include the mass of the ladder. We actually don't need to know the mass of the ladder. This is going to be true for any ladder of any mass that has this particular coefficient with it. So then if I simplify, I get mu s sine of theta min is equal to 1/2 of cosine of theta min. So if I'm going to group like terms, I'm going to need to get the theta min together. So the best way to do that is generally to divide both sides by something similar. So you get like a tangent. Tangent's pretty easy, I think. So if I were to tangent sine over cosine, so like if I was to divide this side by cosine of theta min, and then this side by cosine of theta min, it would cancel out over here. So then I would get mu s, and then sine theta min over cosine theta min is the same thing as tan of theta min is equal to 1/2. So that means that tan of theta min is equal to 1/2 mu s. And then I could take the arctan of both sides, and that will tell me that theta min is equal to tan to the minus 1 of 2 mu s. So if I knew the coefficient of friction, I could then figure out what angle that I would need to have in order to keep this ladder stable. So for example, let's grab my calculator right here. Let's assume that our coefficient of friction was 0.5. So that's, you know, halfway along our one. So if I did tan to the minus 1 of 2 times 0.5, that would be 45 degrees, which the math people would probably figure that out. So that would be a 45-degree angle if my mu s was 0.5. Let's say my coefficient of friction was larger. Let's say that my coefficient of friction was, say, 0.6. What would happen to my angle there? Well, that would give me 50 degrees with a coefficient of 0.6. So what that means is the more friction I have down here at the base, the steeper my angle could be. And that makes sense for the shape of what a tangent function is. So that if you looked at like what the tangent function does is tan of 0 is 0, and it gets very high very quickly as you approach your pi/2 ranges. So therefore you're going to have if your coefficient is very small, you're going to have a very, very high value of coefficient in order to slide. For a regular standard ladder safety, guys, just so you know, I'm going to teach you some ladder safety here. If you're ever having to set up an extension ladder, those are the ones that are just a straight ladder, kind of like we're talking about here. But they tell you the best way to estimate the angle of a ladder is if you stand up and you hold your arms out in front of you. When you stand at the base of the ladder, when you stand like this, that is a good angle for you to have so that your hands are just holding the ladder at the base. The reason they do that is that's actually approximately going to be a 60-degree angle. And a 60-degree angle is a pretty good angle for most surfaces. Obviously, if you were trying to do this on something like ice, you would need a steeper angle. But basically, by having that larger angle, you're increasing the normal force, which then increases the friction force by having that steeper angle. And then the higher you go up the ladder, the more you have to be careful because of the torque that's going to be caused here is going to create a bigger force downwards, causing a torque, causing this ladder to want to slide, to rotate essentially up off the ground. So ladder safety, important. So there's some more examples of this in Canvas. If you need help, there's a problem on your homework assignment. Good luck.